Hello and welcome everybody to the course Crystal Engineering Chemistry Beyond the Molecule. In the last videos we talk about different types of intermolecular interactions and a little bit how we can use it. We talk about general crystals, single crystals built up from one single molecule. We talk about multi-component crystals, so not only one molecule is inside, so two or more molecules are in a crystal, solid solution, co-crystal. These are some keywords. Well, I think now we can try to design crystal structures. Yes. Well, we are going back one step and talking a little bit more about syntons, and then think about how we can use our syntons in crystal engineering, co-crystals. So I mean crystals built up by two components, so binary co-crystals. And when we think about how can we enlarge our strategy designs, and maybe thinking about protocols like the synthetic, preparative, organic and inorganic chemistry protocols, how you can obtain controlled desired co-crystals, binary co-crystals, and higher ordered co-crystals, ternary co-crystals, something like this. Okay. Design and synthesis of crystal structure. Well, if you're talking about synthesis of crystal structure, we are talking about retrosynthesis. So it is similar like in the organic chemistry or the general preparative synthetic chemistry. Synthetic thinking begins with a product, yes, or not with the starting materials. And exactly it's the same in crystal engineering. Retrosynthesis from the viewpoint of crystal engineering: analyze your product, your desired product, in terms of bond connections. And I'm talking about intermolecular bond connections. Don't forget, we always say crystal is a super molecule. Yes? And then try how you can break these connections in small units. I will show you an example from organic chemistry. Synthesis of tropionone. Well, if you look in the literature, you will find a synthesis protocol about 17 steps. Here, if you're interested, here's the product. This was 1906. Around about 10 years later, the scientists said, okay, have a look. No? Look here on the product and think about exactly what I said, so breaking in units, breaking the bonds and thinking about units. And it's really possible, if you break here and you break this unit here, or exclude this unit, and last not least this unit here. Huh? And then exactly you can obtain the desired product directly in one-step synthesis. This is retrosynthetic approach. And this is a typical approach. I would not say always, and this will not be optimized, and mostly you're thinking about a retrosynthetic approach. Well, and if we try to break the bonding when we are talking about syntons once again. And also syntons is not coming from crystal engineering, it is coming from organic chemistry. This keyword was established in 1960 by Core. This is an organic chemist. The smaller substructural units that are generated by disconnecting the targets. And he said, well, it must be representative, such a synton, such a small unit. And then you can use it to build up, or you can use it in reaction synthesis for desired molecules. And related to this keyword from organic chemistry, supramolecular syntons were established in 1995 by Desiraju Gautam. Similar role. When what he said is he introduced the keywords nodes for molecules and node connections for the interactions. Yeah? The molecules and the interaction, both together. This is a supramolecular synton. And during our lecture series, we have seen several syntons, and we divide it in two classes. Well, we have, as I said, we have two different types, homosyntons. We have shown carboxylic dimer, for example. See it here. We have a dimer, but once again, don't forget, only 33% of all crystal structure in the crystal structure database show with dimer. The other 66% are forming, I don't know, for example, catemer, you see it here, or something else. Or another very nicely homosynton is something like this here with syntons of 2,1,4-benzoquinone molecules. On the other side, there are heterosyntons. Here, this is how you see it. Formed, for example, two amide units here. In this case, with a CO double bond with an NH, amide. This is heterosynton, very nicely. And it depends of the molecular structure. Sometimes you have a 2-point or 3-point recognition here. You see it here. In the case, you have first with amide, 2 times the amide, intermolecular interaction. Here you see additionally NHN, 3-point. Or our PP intermolecular interaction, we started with this interaction, one of the first slides of the lecture series, also heterosynton. Another, for example, we have seen very nicely this halogen nitro intermolecular interaction. All of them are called heterosyntons. And you can use both homosyntons, heterosyntons. Sometimes it's a competition, sometimes, how shall I say, you can use both together, synergetic processes. We will have a look. For example, if you mix nitrobenzoic acid with an aminobenzoic acid, what do you think? What do you get as co-crystal? What are the units? Once again, nitrobenzoic acid and aminobenzoic acid. This is very nice. You see it here. This is a chain. Do you see the nitrobenzoic acid with nitro substituted acid? And this is the amino substituted acid. And in this case, you have a heterodimer, or a heterosynton, you can say. And in this case, you have a homosynton. This is a very nice example because once you can use both. This is not a competition. Yes, not a competition between a homo and heterosynton. And in the second, thing is very nicely examples to show insulated chemical functions. So this is only possible because we have a 1,4 position of a substituents. No? I'm sure I didn't check it, but I'm sure you will not find such chains or such units, not chains, but such pattern in the case of a 1,2 or 1,3 position of substituents. No? Very nice example, insulated chemical function and synergetic possibilities of homo and hetero syntons. Well, but one aim in crystal engineering is discovery of new supramolecular syntons. Question is, what are suitable new supramolecular syntons? This is really a big deal. Robust and directional supramolecular syntons. This is the aim. No? Robust and directional. And especially this directional is very important. You know, for example, we have shown in the past, no? Going back here, talking here of a iodine nitro synton. This is very important. In this case, directional. In this case, when you look to a substitution pattern, no? Different molecular systems can give very similar crystal structure. We talk about similarity. And an opposite, very similar molecules, substituents, 1,4 position, 1,3 position, 1,2 position, can crystallize in extremely different ways. So, keep this in mind, thinking about suitable new supramolecular syntons. Question is, are there some rules or something like this? No? Yes. So, I would say suitable synton occurs more frequently in a given group of compounds. Frequently in a given group of compounds. More frequently. If you get one crystal structure with an interesting intermolecular interaction, when this is not directly a supramolecular synton. A synton, think about what I've said from Corey, introduced syntons and Desirajo. Syntons are units to build up crystal structure, and not only one crystal structure. You can use supramolecular syntons to build up general or a lot of similar crystal structure. So it's absolutely necessary that a synton will occur very often, or more than 1 or 2 or 3 times in crystal structure. Then it's strange, and the directionality is very important. Only one type or one special position, only one very special crystal structure, an intermolecular interaction, which is randomly directional in this crystal structure, is not enough. And you need this function, it must be a functional group which will be seen very often, or not only once. If you must crystallize, if you must synthesize a functional group, very special, very crazy, spacey functional group, this is only helpful for one special task, the crystal structure, when it does not really make sense to use it in crystal structure synthesis in general. And it must be really easy to introduce a new molecule. Okay? Go. Okay. When we must talk about the size. The syntron combines an economy in size with a maximal of structure information. What does it mean? For example, if you look only for interval of hydrogen bonds between hydroxy group, well, this is nice, okay, it makes sense. But it must have a little bit more specific information. Such information is not really useful to efficiently planning in crystal engineering. This is more a general feature. Well, on the other side, if you have a really large syntron, where a lot of information inside of a whole crystal structure, of a whole unit. If a unit is a large unit, you can build up a very, very specific crystal structure. This is possible. But on the other side, if a really large syntron is only useful in some cases, so it is not observable very frequently. Well, we have once again only hydroxy group. This is too small, it's not specific. On the other side, large syntrons, well, this exclude a lot of structural features. So always the same, the golden midway, you can say, somewhere between. You have a small syntron with a maximum of useful structure information. This is nice. This is our aim to find. Okay. Well, with all this information in mind, we will think about co-crystal synthesis. Okay, how can we use it? We have heard so many things. You got a lot of information of intermolecular interaction. And we have seen we have strong hydrogen bond, we have weak hydrogen bond, strong halogen bonding, weak halogen bonding, and so on. And you see there's a hierarchy based on the energy and the strength of intermolecular interaction. And this can be used for hierarchy of intermolecular interactions. Can be used to try to develop a strategy or a protocol for co-crystal synthesis. Well, what is important? Selectivity, construct supermolecules with predictable connectivities. Predictable, this is very helpful, it must be predictable. The second point, versatility. Yes, assembly process under different reaction conditions, different solvents. Well, it depends on the solvent. Sometimes you can have a competition between the reaction. Sometimes it doesn't matter. It's independent of the solvent, but you should think about this. The versatility and yield. Frequency of occurrence of a specific molecular recognition, the presence of other potentially intermolecular interaction. Yes, this is not only once you will get with crystal structure, sondern frequency of occurrence of this pattern, this molecular aggregation pattern. You will see more than one time. Now, try it. First of all, don't forget we have always a balance of competition between intermolecular interaction. And so, the balance and competition is very important talking about hierarchy. And, well, with competition, if we have a competition, we have a mismatch of acceptor-donor, and then our outcome is less predictable. So it's very important think about with competition. I will show you for examples. Well, you have here two components. The central unit X, one component, and the central unit epsilon in the second component. Central unit X has two functional group as acceptor, A1, A2, and functional group, and the unit epsilon has two donors, same donor. No? And this is typical for competition. If A1 is significantly stronger, better you can say, than A2, then you will get something like this. So intermolecular interaction of A1 with a donor of both sides. No? If it's not stronger than A2, then is what we're talking about compounds, competitive compounds. No? Well, in this case you see it here, A2 with donor, A2 with donor, or A2 with donor, A1 with donor, and so on and so on. No? So the strange is very important, first of all. No? So in the practice, for examples, if you, it's very often you can see with here such intermolecular interaction of hydroxy group with an aromatic nitrogen center of a hydroxy with cyano group, or only hydroxy with N, always dominate over hydroxy. Yeah? This is, for example, one experience we have from the crystal structure database and the crystal engineering. No? You can use it. No? You see it very nicely. For example, I have an experiment with cyanoproteins and phenols. Cyano here, pyridine here, and phenols also. Or everything's. When you will see that exactly the first here of the syntons, these units are mostly favored. Good. Hydrogen bonds and halogen bonding, both can be used as in a partnership. But once again, thinking about here the competition. Here, thinking about the competition. But it's very important that we have different strengths. Not comparable strengths. No? And very nicely here in a sketch, what we have here seen, with this co-crystallization, what you have here, a 2-point homomeric hydrogen bond, and additionally here, second single point halogen bond, this is one here. Homomeric, and here second single point. I will show you some examples. We are starting here, once with amide function, amide here, amino here, and here also amino, and all of them have here and aromatic nitrogen. Amide, aromatic nitrogen, amide, aromatic nitrogen, amine, and also aromatic nitrogen. And well, first you can build up very nicely hydrogen bond units. For example here, amide here, okay? And here I have amino hydrogen bond with here the nitrogen of a system. This is also both are very typical, amino and with the nitrogen. It's all the same like here. Well, so this is the first step, no? Hierarchy. First, as use the most stable unit. Okay, and then the second step, here, adding our halogen bonding donors in this system, which is very typical halogen bonding systems. No? You have a more or less fluorinated aromatic systems with 1 and 2 iodine species. It's very often used in crystal engineering, such systems. What you get is here, once again here in the middle, are our homomeric systems, and here you see here our halogen bonding. Additionally here, nitrogen, iodine, nitrogen, iodine, nitrogen, iodine, and also here nitrogen, iodine, building this halogen bonding. Okay. Another is, we talk about homomeric hydrogen bonds. Now we are talking about heteromeric hydrogen bonds. Here, this is our heteromeric hydrogen bonds. And similar like in the last examples, the strategy I would say, the single point halogen bond. Heteromeric, and here the single point. Have a look. Here we see directly we have our amino function, and now we have a carboxylic acid on this side. Amino function, carboxylic acid also on the side here, and very nicely acceptors, halogen bonding here, halogen bonding here, halogen bonding here. Okay, first we have this heteromeric synton here. Here our amino function and the carboxylic acid, and here exactly the same. And now adding our halogen bonding donor, here the iodine, and exactly like the last pattern, very nicely build up a ternary co-crystal. No, this is a binary co-crystal, sorry, binary co-crystals. Good. Next point, trying to use insulation of a robust synton. Yes, for example, isonicotinamide with carboxylic acid. This is very, very typically using isonicotinamide in crystal engineering. Have a look here. What we have, a 2-point NHO interaction. You see it here. This is what we're calling this amide synton. Here very nicely. And this isonicotinamide has this nicely nitrogen center here, aromatic nitrogen center, which allows the formation of an additional hydrogen bond to carboxylic acid. Okay. This looks very nicely, and but there's a problem. What is the problem? Because if you look in general of amide, you have an amide function here, and here a carboxylic acid. Well, you have a competition of amide and acid amide. And we talk about you must avoid competition, or try to think about how you can handle this competition in general. You have, in this case, definitely in competition. And you look, for example, the crystal structure database. It's now in this version 5.41. This is version of 2020. You will find around about 130 entries with interaction of amide, isonicotin amide. So mostly this type of interaction is preferred. Okay, exactly this. But additionally, we will find round about 30 entries of isonicotinamide acids. Here is our amide, and here is our amide carboxylic acid unit. And also, if we're playing with such systems, isonicotinamide with acid, one, it could be happen that you will find carboxylic acid dimers in the system, or additionally, exactly what I've seen here with 1 point, here, such systems. So this is always could be a problem, not always, but could be a problem, and always in this case should be very carefully thinking about. So preferred, favored is isonicotinamide, but on the other side, it is very often found here such mixed systems. And well, how can you favor? For examples, increasing amount of isonicotinamide favor amide homodimer, exactly what I've seen. High concentration or the ratio, playing with a ratio. Or on the other side, you can play with electron density, with basicity and the acidity. You can play with the properties, tune the properties for your compounds. Substitution of pyridine by heteroaryl moieties with low hydrogen bond accepting. This is for an acceptor. On the other side, increasing hydrogen bond donor strength of acids when you will get acid amide heterodimer. Okay? I think this is a very nice example that is always important to look very carefully to the use systems and think about what different types of syntons and products could be obtained and how you can control it. Okay. And in summary, you directly see from this last slide, we have a little understanding and control for thermodynamic and kinetic factors in the choice between a homomolecular and heteromolecular recognition process. Very often, it depends extremely from a molecule. We have seen. On the other side, if you look in the crystal structure database, you will see some trends. So in general, what you see, for example, the space group symmetry, in the case of co-crystals, you have a strongly increase of a space group P1 bar. That means we have, really from around about 33% to more than 40% in the crystal structure database. We see a slightly increase of P21C and C2C, and on the other side we observe a decrease of chiral space group. It makes sense. Very often you will not see a chirality if you have a co-crystal. Not always, but very often. And we talk about Z prime, you remember, in this video dealing with deuterium. We talk about Z prime. In the case of co-crystal, very often you have Z prime as 1, so both molecules, if you're talking about binary co-crystal, both molecules are in the subunit. And what you see is, if you look to the units, we observe, well, very often we see the acid as a donor. Very often, around about half of a co-crystal, you have acid as a donor. And on the other side, very often with aromatic nitrogen is very often acceptor. Hydroxyl group very often as an aromatic hydroxy group in phenol, you will see as a donor, and our amide also. The question is, how can you distinguish between a salt and a co-crystal? Well, you can say I make a crystal structure analysis, single crystal structure analysis, but very often, well, you are not able to get single crystals, or you have not the possibility to measure, and so on and so on. So you have a crystallization product, a powder, and you will check very rapidly, is it a co-crystal or is it a salt? And one utility or one spectroscopic method very helpful is IR spectroscopy. For example, here we have intensity, we have the values here, the wavelengths, and this is amine with a co-crystal, the amine salt. And here you see directly, this is the interesting region where you should have a look. The case if you have a salt, there's nothing. Starting here, if it's starting with a starting product, the amino vibration mode. This is interesting. This is free amine. In the case of a salt, it's the void. You see no vibration mode. No? In the case of a co-crystal, you see in vibration mode, but it's shifted. You see it very nicely. Well, IR spectroscopy is a very helpful method to distinguish between the different products.